Welcome back to the sixth and final section of Chapter 3. This section, mathematically, is a lot of it's just an application of what we've already done with solving exponential functions. And I was very tempted to kind of skimp on it just a little bit. However, I decided not to. You're welcome. Uh, because application-wise, this is huge. I know that one of the things you constantly hear is, oh, why don't we ever learn how to balance a checkbook? Well, you don't learn how to balance a checkbook because nobody actually balances their checkbook anymore. And why don't we ever learn about like mortgages and stuff? That's this section right here. So we're gonna look at it definitely nice and in depth so that you can learn all about mortgage payments and interest and stuff like that. So I kind of like that they broke this out as its own section instead of just having the compound interest as a little subpart of a different section. So our learning targets for today: find the amounts accumulated using compound and or simple interest, find future values accumulated in annuities, find present values of loans, find periodic payments for annuities and loans, solve applications involving finding interest rates and times for loans and investments. So lots of nice, fun, big words in this one. So the first thing we're going to look at is simple interest and compound interest. And we're going to look at the similarities and mostly the differences. So a simple interest in this column right here, we're always going to, like every year, we're going to add our interest. So we start out with our principal. That's what we start out with. So say $100, and we have an interest rate of 5%. So the first year we're going to add 5. And the second year we're going to add 5. And the third year we're going to add 5. So we're going to add 5 for however many years. Eventually we're going to have like $1,000 in this account, and we're still going to add $5 every year because that rate is it's that same thing. So this simple interest is a very linear growth pattern. Compound interest, so if we start out with $100 and the first year we're with an interest rate of 5%, the first year we're going to add $5. Now the second year we have $105. 5% of that is not $5, it's a little bit more than that. And so we're going to add that little bit more. And then we're going to add a little bit more the next year because we have 110 plus a little bit. And so 5% of that is going to be 550-ish. And then we're going to add 5% of that and continuing. So the amount that we add will continue to grow. So it'll always be the percentage of whatever it is we have. And that is an exponential function where we have the amount is going to be the principal times 1 plus the rate as a decimal to the nth power. Now the as a decimal part is what gets people a lot. It causes problems because 5% would be 0.05. So this would be p times 1.05 to the n. And so this is just our interest compounded annually, the formula. It's the same thing we just saw. So we have the fixed interest rate is R, the principal is P, N years because it's N. Technically it doesn't have to be years, but being that R is going to be an annual rate, N does need to be in years. And so a problem or a comparison here, let's say George Milligan invests $5,000 at 5% annual simple interest, and Quan Li invests $5,000 at 5% annual compound interest. Compare the values of both investments after 10 years. So we're just going to plug these into the equation. So George is going to have his principal is 5,000, and then times 1 plus n, which is 10, times the rate, which is 5%, so 0.05. And we can do that calculation. 10 times 0.05 is going to be 0.5. 1 plus 0.5 is going to be 1.5 times 5,000 is going to be 7,500. So George Milligan will have 7,500 after 10 years. Quan Li, we're going to have the amount after 10 years will equal the principal, which is 5,000, times 1 plus 0.05 to the 10. So 1 plus 0.05 is 1.05. To the 10th power is going to be a bit of a decimal, and then times the 5,000 gives us 8,144.47. 144.47. So yes. So as we can see, with the compound interest, even over just that 10-year mark, Quan Li earns almost $650 more than George Milligan, because it keeps you keep adding more and more every year instead of adding the same amount every year. So that's what compound interest looks like. Most things are going to be compound interest. Sometimes it's annually, but a lot of times it's not going to be annually. It's going to be quarterly or monthly or something like that. So what do we do if it's compounded more than one time per year? So k times per year. We have to adjust the formula just a little bit. We have to take that rate and divide it by k, because we don't get 5% every 3 months. We get a total of 5%. And then, since that splits the year up into multiple things, we would then have to multiply by that k so that we have the right number of time periods. So the formula is slightly different, but we're still just going to plug stuff into the formula. So an example, suppose Roberto invests $500 at a 9% annual interest compounded monthly, so that's 12 times per year, that's the K. Find the value of investment 5 years later. So we're looking for A equals his principal, that's $500, that's his initial amount, times 1 plus 9% is going to be 0.09 over 12, because he gets 9% annually, so it's 9/12% every month. And then to the 12 times 5, because now we're counting every month, and so we don't want to count every year. We need 12 times 5 so we have the right number of time intervals. And from here, it's really just plug it into the calculator. 0.09 divided by 12 is a number, plus 1 is 1 point a number. To the 12 times 5 is 60, so we go that 1 point something to the 60th power to get a number, and then finally we multiply by that 500. So from here to the next step is just click, click, click in the calculator, and what we get after 5 years is $782.84. So over that 5 years, he made $282 by just having it sit there. Um, and so that's one of the things we can find. We can find that amount at the end of a certain time period. But we could also find other things. Judy has $500 to invest 9% annual interest compounded monthly. So same basic setup. How long will it take for her investment to grow to $3,000? So now we're looking for how long will it take? We're looking for the T. So the annual rate, or the amount, sorry, A is going to be $3,000. That's what we're looking for. Is going to equal $500 times 1 plus 0.09 over 12 to the 12t. We've done problems like this already. We did them in the last section. To solve this algebraically, we're going to want to divide by 500. So we'd get 6 equals 1.09 over 12, which is about 0.0075. So 1.0075 to the 12t. And now we could take the natural log of both sides. You could take the regular log as well, but I always go natural log. Natural log is way nicer in calculus, and so being that it doesn't matter, I always gravitate towards natural log. So we have the natural log of 6 equals 12t times the natural log of 1.0075. So natural log of 6 is a number, natural log of 1.0075 is a number. We can divide those along with a 12. So t will equal natural log 6 over 12 times natural log of 1.0075. And we end up with t equals about 19.98 years. So in 20 years, that $500 jumps to $3,000, which doesn't sound like a lot. I mean, ooh, you made $2,500 in 20 years. Well, that's for doing absolutely nothing and assuming that nothing else was added to that account. But it multiplied by 6 in 20 years. So imagine if you had more than $500 to invest. We can check this graphically. To check it graphically, we would plug this into like y1 and this one into y2 and graph it, and then we can find the intersection to see that, oh, hey, look, it's the same. So we can check it graphically. So we found the amount after a time. We found the time it would take to get a certain amount. What about, now we're looking at Stephen. He also has $500 to invest. What annual interest rate compounded quarterly, so 4 times a year, is required for him to double his money in 10 years? So we have 4 times a year instead of 12. And we're looking for the interest rate now. So we're looking for R. So his principal is still 500. And we'll have 1 plus R over 4 to the 4 times T. We want 10 years. But now we need the amount. What amount will he have? Well, he wants to double. He starts out with 500, so he'll end up with 1,000. All right, how do we solve for this? We're going to solve for this similarly to what we did last time. Our first step is we're going to divide. So we get 2 equals 1 plus R over 4 to the 40th. And now we do have a couple different options here. Solving graphically, like we could graph these and see what that r would have to equal. Another thing we could do is we could take the 40th root. What would the 40th root be? That would be 2 to the 1/40th power will equal 1 plus r over 4. 2 to the 1/40th power is going to be a pretty small decimal. Well, I mean, it'll be 1 point something. Then we'll subtract 1 to get 0.00 something. We're going to multiply by 4. I mean, this is all calculator stuff at this point, but we multiply by 4 then to get r is going to equal 0.0699, which would be 6.99%. So if he has a 6.99% interest rate compounded quarterly, he should double his rate in 10 years. Now, if it was compounded monthly, do you think the rate would have to be lower or higher? A lower rate would actually work because you'd get to be taking percentages of bigger numbers quicker. So the more it's compounded, the lower the rate needs to be. And so, and that goes, we can keep going until we're compounding continuously. So we had quarterly, monthly, like daily, that would be 365 times. We go to compound continuously. Now, when we do that, what we notice is that 1 plus r over k, if r is constant and k is going to infinity, and then to the k, we find that this becomes asymptotic, and it gets closer and closer to 2.71, which is e. That's actually where the number e comes from. And so when we compound continuously, we get a equals p times e to the rt. It's an easier equation, which is nice. We can have stuff compounded continuously in finance. Generally, we don't, because you'd make way more on interest than you would if it's compounded monthly or even daily. But this happens a lot in nature. Like our exponential growth and decay functions look like this. Half-life functions look like this, like radioactive decay. So this is just another application for our compounded continuously stuff. So if we have an example, suppose Sarah invests $100 at 8% annual interest, compounded continuously. Find the value of her investment at the end of 7 years. So A equals our principal was 100. E to the R is 8, so 0.08 times T, which is 7. 0.08 times 7. E to that power, and then times 100. Sarah will end up with $149.18 at the end of those 7 years. So with 8% interest compounded continuously, she made $50 almost. And so that's just another type of interest rate or interest. So we have our two types. We have our compounded k times per year, gets that equation, and then compound continuously gets the other equation. So that's just a quick little recap of that. As we were talking about the one with Stephen, looking at what would he get more or less than someone that was compounding every 12 months, brings us to the annual percentage yield. The annual percentage yield is a way of comparing different rates and compounding things. So what the annual percentage yield is it takes it all to what rate would it be if it was compounded only once per year. So what would the rate be if it was only compounded once per year? So how do we find something like that? Well, let's say Logan invests $2,000 with Coastal Community Bank at a 5.15% annual interest compounded quarterly. What is the equivalent APY? So what we can do is our rate with the compounding, we have $2,000 times 1 plus the 0.0515. It's compounded quarterly, so that means 4 times a year, to the 4 times 1, because we're just looking at 1 year. It's a 1-year span. We want that to be equal to, what rate would it be if it was just compounded once? So that would be $2,000, the same principle, 1 plus the rate. We don't know the rate. And then to the 1, because it's still 1 year. So to find this, the very first thing we would do is divide by the principal. The principal is the same in both cases, so we end up with just 1 plus x equals 1 plus 0.0515 over 4 to the 4th power. So something to notice here is that since the principal divided out right away, that actually has no impact on the problem. The annual percentage yield depends entirely on the interest rate and the number of times it's compounded per year. And so then the next step, we just have to subtract 1. I know this equation looks like it's going to be tough to solve. Well, the only x is right here. So we subtract 1. This is just a calculator problem. X equals, we can go 0.0515 divided by 4 plus 1 to the 4th power and get 1.0 something, and then subtract that 1 to get 0.0525. So a 5.25% annual interest compounded once will give the same APY. And so this is useful if, let's say, we had Logan invest his $2,000 at 5.15% compounded quarterly, and Henry invested his $2,000 at a different bank, Chase, for 5.1%, but it's compounded monthly. We could find the APY of both to see which one would actually be a better investment. So it allows us to compare apples to apples. So that's where the APY comes in very handy, and a lot of times it will be reported. Like, you don't even have to calculate it every time, but that's what it is. You'll see it with loans, interest. You'll see it with credit cards, give you an APY value or an APY percent to let you know what that percent is. The next piece is 2 things that are very, very similar. The first is annuities, which is a future value. So we were looking at interest. It's being compounded every month, every year, every quarter, whatever. But everything that we've looked at, we've put a chunk of money in, and then we just left it. Chances are that's not what you're going to be doing. Chances are you're going to be putting money in every month, every quarter, every whatever it is you're putting into it. And so it's going to get more than just the interest that it's accruing. So that's where this comes in. Now, if you're compounding every quarter, you might be putting in money every month, and that complicates things a bit. It makes the equations a bit um, tougher to manage because the stuff you'd put in at the end of the first month, you'd only get the interest on that for the 3 months that it's in there, and it's kind of weird. So we're going to use ordinary annuities where the stuff you'd put in would be put in at the end of each period. So it just simplifies it a bit, like quite a lot. Um, and so that's what annuities are. The other piece, which is actually an annuity, is loans and mortgages. And that's looking more at the present value. And so a loan and a mortgage, like I have a mortgage on my house, I owe the bank a lot of money, and I pay it off. I don't pay off every little bit of it. Like if I had the full chunk and was looking at the percent, like the interest on it, like I would not be able to even pay the interest for the amount that's paid that I owe right now. What they do is they take it over the course of the mortgage, which could be a 10-year, 15-year, 20-year, 30-year, and they figure out how much it's going to cost for that whole amount, and then they divide it up by the total, by the number of payments that are going to be made. So um, my payments, even though my loan amount's going down, my payments will stay the same throughout the course of the loan, assuming I don't do anything to adjust it. Um, and so that's where that comes in. And the equations are very, very similar. So the annuity is the future value. We have payments of our dollars. We're always putting in the same amount each time too. We're not randomly putting in different amounts. Again, that would complicate things. This is a simplistic version of it. Times 1 plus I, the interest rate is now I instead of R for rate, it's I for interest. To the n minus 1, then divide by I. If you look in the book, it'll show you where that calculation comes from if you're interested in that, but who knows. And then the mortgage and loan, the present value of an annuity, because it is an annuity, it's the same thing. We're consistently paying on it and stuff. It's R and then it's 1 minus the 1 plus I to the negative n over I. So the difference is the future value tends to be increasing. Like you're making payments and you have that positive interest. In the present value, you're working on paying something off. You're making it go lower. So let's see how we can look at these. The first one, at the end of each quarter, Emily makes a $500 payment into the Langahan Mutual Fund. If her investment earns 7.88% annual interest compounded quarterly, what will be the value of Emily's annuity in 20 years? So we start with our equation. So our future value will be the amount she's paying in. That's $500 times 1 plus the interest rate. So it's 7.88%, so 0.0788 to the n. So it's in 20 years, but n isn't the number of years. No, 0.778 divided by 4. That's the interest rate per compounding period. So that divided by 4, and then the n is the number of compounding periods. 20 years times 4 gives us 80 years, minus 1, over the 0.0788 divided by 4. Now this looks ugly, but it is just a calculator problem. we can, the 0.0788 divided by 4, just a number. 1 plus that is a number. To the 80th power is a number. Minus 1, number. Divide by that 0.0788 over 4. Then multiply by 500. And we get, after 20 years, we get that Emily is going to have $95,483 and some change, about 39 cents. And so, I mean, that's a lot different than just the interest alone, but remember, she's adding money to this. And so if you think about it, she's adding $500 4 times a year. So she's adding $2,000 a year for 20 years. So $2,000 for 20 years, that will give her $40,000. So she made $40,000. If she would have took that and stuck it in a mayonnaise jar and buried it in her backyard, she'd have $40,000. Instead, she has $95,483. So that's where the annuities and investment can really make a difference. If you ask, how can you be a millionaire? Well, you could figure out, you'd put $1 million in your future value. You don't really get to change the interest rate, but you could figure out what this payment is going to be to make it $1 million. And so, anyway, that's how you can look at annuities. And again, this is a very simplistic thing. She's always putting in the $500 at the very end of the period, and it's always the same. So it's a very consistent thing. This is how retirement accounts work and stuff too. So now, loan and mortgage. So Carlos purchases a pickup truck for $18,500. What are the monthly payments for a 4-year loan with a $2,000 down payment if the annual interest rate is 2.9%? So we're going to figure out what is that R value. And so to do that, we first want to start out. So he's not paying off $18,500. He started out with $2,000 down, so we have to subtract that off the top right away because his loan amount is going to be $16,500. And that's going to equal R. So if you want to figure out how to be a millionaire, it's going to be the same process with the annuities as we're going to do here. So then times 1 minus 1 plus I, so 0.029 over, and he's paying monthly, so 12, to the negative what am I missing? It's how long is, 4-year loan. That's what I'm missing. That was the number. I was looking for the time. So 4 times 12 is 48. Negative 48 over 0.029 over 12 again. So this is basically the same. So now, in this case, we're going to figure out what this big nasty number is, because it is something horrible. We go 1 plus the 0.029 over 12, and then we take that to the negative 48. We go 1 minus that number, and we divide it by that 0.029 over 12 to get something not pleasant. And then we're going to take that 16,500 and we're going to divide by that number we found to get R equals 364.487. And so what that means is that he's going to be paying $364.49 for 47 months, and then he'd have just a little bit less in that 48th month. But $364.49 per month would be his car payment. That's how you can find that out. A house mortgage is going to be basically the same, except that your PV is going to be a lot more. And then also your number of years is probably going to be longer than 4. So the numbers just get bigger, but that's about it. So, again, it looks like complicated math, complicated formulas, definitely. Um, the compound interest formulas and stuff at the beginning of the chapter, or at the beginning of the section, yeah, you should know those. You should be fairly familiar with those. These guys, I do not expect you to memorize these. I mean, right now you're at home, so you have your book, you have that kind of stuff. That's right there for you. Um, if you were in class and we were taking a test or something, I would give you these formulas if you needed them. That is not something that I would ever have you memorize for this class specifically. But again, I wanted to do it because this is a very applicable thing. A lot of you are probably thinking about getting a car at some point in the near future. You might be taking out a loan. So there's your payment. Um, so I will see you guys in class though. But until then, keep working problems, keep asking questions, and as always, happy mathing.